In this exercise, I'm going to be showing you how to calculate the area of a segment of a circle using double integration and polar coordinates. I'll demonstrate how to define the region in terms of integrals, and if you stick around until the end, I'll show you how to evaluate the integrals. We have a circle which is cut by a vertical line, creating a segment shown here in red. We are tasked with finding the area of the segment shown in red using double integrals and polar coordinates. We could use the equation to find the area of a circle sector and subtract a portion of the blue region to do this, but we'll use this to verify our solution. The equations of the vertical line and circle are shown in Cartesian coordinates. The circle has a radius of 2 and is centered at the origin. Its equation is x² + y² is equal to 4. The vertical line has an equation of x equals 1, which means it cuts the x-axis at x equals 1. The first step in finding the area is to convert the equations of the circle and the vertical line from Cartesian coordinates to polar coordinates. To do this, we'll substitute rcosθ for x and rsinθ for y. Beginning with the circle, we have an equation where x² + y² is equal to 4. And making the substitution for x and y gives r² into the bracket of cos² plus sin² is equal to 4. And using the trig identity where cos² plus sin² is equal to 1 leaves r² equal to 4. And taking the positive square root of both sides of the equation gives r equal to 2. And now for the vertical line we have x equals 1. And making the substitution for x gives rcosθ is equal to 1. And therefore r is equal to 1 divided by cosθ. Now that we've found the radial distance r for the circle and the vertical line, let's look at the behavior of r as we use it to compute the region shown in red. As r rotates in a counterclockwise direction between, at this stage, unknown angles of theta, where theta is the angle r makes for the x-axis, the radial distance covering the area shown in red is determined by both the vertical line and the circle. The radial distance begins when the vertical line intersects with the circle for the first time at some unknown angle of theta and ends when it meets the circle. This process continues until it reaches another unknown angle of theta. To find the angles of theta where the circle intersects with the vertical line, we can equate the polar equations. We have two polar equations, r equals 2 and r equals 1 divided by cosθ. If we equate the two, we get 2 is equal to 1 divided by cosθ, and cosθ is equal to a half, and therefore theta is equal to cos to the -1/2. Due to the periodic nature of the cosine function, in this example, theta is equal to -π/3 radians and π/3 radians. So when the vertical line first intersects with the circle, theta is equal to -π/3 radians. And then when it intersects with the circle for the second time, theta is equal to π/3 radians. Due to the symmetry about the x-axis, we could consider the area between theta equals 0 and theta equals π/3, and then double this area to get the total area. But for this exercise, I'm going to consider the total area. Now we understand the region as the radial distance r rotates about theta, we can define the limits of integration of the outer integral. We saw that when the vertical line intersects with the circle below the x-axis, theta was equal to -π/3 radians. And then when it intersected with the circle above the x-axis, we saw that theta was equal to π/3 radians. So the limits of the outer integral run from theta equals -π/3 to theta equals π/3. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance or in the r direction. This will help us define the inner integral. When we integrate in the r direction, this will represent the inner of the integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. And so dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate along the radial distance r, we begin at the vertical line, so where r is equal to 1 divided by cos theta, and continue until we reach the perimeter of the circle, so where r is equal to 2. So now we can add the limits of integration of the inner integral, so that's when we sum or integrate along the radial distance r. We can see from our diagram that our lower limit is at r equals 1 divided by cos theta, and our upper limit is at r equals 2. And we are summing infinitesimally small pieces of area dA, which translates to r dr d theta. We can now begin to evaluate the integrals. So beginning with the inner integral, we need to integrate between r equals 1 divided by cos theta to r equals 2 r dr. Using the power rule, the antiderivative of this is r squared divided by 2. And plugging in the values for r, we get 2 minus 1 divided by 2 multiplied by cos squared theta. We can now start work on the outer integrals, of which we now have 2. And beginning with the first, we want to integrate between theta equals minus pi by 3 radians and theta equals pi by 3 radians of 2 d theta. And using the power rule, its antiderivative is 2 theta. And plugging in the values for theta, we have 2 pi divided by 3 minus 2 pi divided by 3. And this equals 4 pi by 3. And for the second of the outer integrals, we want to integrate 1 over cos squared theta d theta between the limits of theta equals minus pi by 3 and pi by 3 radians, and then multiply this result by a half. And the antiderivative of this is 1/2 multiplied by tan theta. If you'd like more details on how to evaluate 1 divided by cos squared theta d theta, please see this video. And plugging in the values for theta gives a half into the bracket of root 3 minus root 3, and this equals root 3. So now we have the area of our segment shaded in red, which is equal to 4 pi by 3 minus the square root of 3. So now let's verify this solution. We can verify our solution by calculating the area of the sector of the circle and then subtracting the area of this triangle here and this triangle here. The area of the sector is the angle it makes as a fraction of 360 degrees multiplied by pi r squared. So the angle it makes is 120 degrees, so divided by 360 and multiplied by pi r squared, where r is equal to 2. And this gives the area of the sector to be 4/3 pi. And the area of one of these triangles is a half multiplied by the base multiplied by the height. So we can see the base is equal to 1 because we know that the vertical line cuts the x-axis at 1. And we have the radius, which is 2. So we need to work out the height. So we can use Pythagoras to work out the height. So it's the square root of the radius squared minus the base squared, where the base is equal to 1. So the height is equal to the square root of 3. And so the area of one of the triangles is a half multiplied by the base multiplied by the height. So we have a half multiplied by 1, which is the base, multiplied by the square root of 3, which is the height. So that gives the square root of 3 over 2. So the area of the segment is the area of the sector, which is 4 pi by 3, minus the area of the two triangles. So minus root 3 over 2, minus root 3 over 2. And this gives us a final answer of 4 pi by 3 minus the square root of 3, which verifies our solution.